So the unit circle had a circle of radius 1 at the origin. And we said if you took any angle, theta, you would define on the terminal ray of that angle, the point of intersection with the circle, the coordinates to be cosine theta, sine theta. That made cosine theta and sine theta a function of what angle you put in, since for each angle you had one value of each of these. And furthermore, we could define other trig functions, right? So sine theta was the y coordinate, cosine theta was the x coordinate, tangent theta would be y divided by x. And then there were three reciprocal functions. Cotangent theta was this one upside down, x over y. Secant theta was this one upside down, 1 over x, and cosecant theta was this one upside down, 1 over y. There are 6 trig functions, and we'll find out maybe at the end of the day that these correspond to the 6 ratios of sides in any right triangle, actually. And so it's really useful for solving triangles, because this tells you how to, by similar triangles, effectively solve triangles quickly. All right. Also, we had trig identities. If you dropped a perpendicular here and made this reference triangle, we found out that sine squared theta plus cosine squared theta is always equal to 1. This is the famous Pythagorean identity. I'll just remind you of the proof, see if you forget it, right? This works in all the other quadrants too, but it's most easily drawn in the first quadrant. If you draw the angle theta here and drop this perpendicular right here, this is x and this is y. And this is 1 because it's a unit circle. I should have put that on here also, 1. This side squared plus this side squared equals this side squared. Well, that's what this is. Y squared plus x squared equals 1. And the unit circle is the same as this one. So it's proved by the Pythagorean theorem. Hence it's called the Pythagorean identity. Then we also had, because of these relations, right, for the reciprocal identities, that the cosecant theta, since it's defined to be 1 over y, is also 1 over the sine theta. The secant of theta, because it's defined to be 1 over x, the x coordinate, is also 1 over cosine. And the cotangent of theta, since it's defined to be x over y, is the reciprocal of y over x, which is tangent theta. Then these things are always reciprocals of each other. So we also write that sine theta equals 1 over cosecant theta. Cosine theta is 1 over secant theta. And tangent theta is 1 over cotangent theta, because they're reciprocals of each other. However, there are some angles for which some of these are not defined. For instance, if you take a 90-degree angle up here, you get the points x equals 0, y equals 1. You try to divide by x, you get a division by 0. So at the 90-degree angle, the secant and the cotangent are, secant and the tangent are both not defined. The ones that divide by x when x is 0 are undefined. So sometimes one side of this will be defined and not the other side. Therefore, usually instead of calling these theorems, although you can call them that, it's fine. We usually call these identities, meaning that they're always true when both sides are defined, when everything's defined in here. So sometimes this one will be division by 0, but this one will be defined to be equal to 0. And so you just have to realize that when both sides are defined, these are always true, but sometimes one side is defined and one not the other. So we'll call them identities. These are the reciprocal identities. Express reciprocal relationships. And Moreover, we then divided this one by cosine squared, and we've done it again. The Pythagorean identities we found are this one here, which we got from the unit circle. We divided this through by sine squared or by cosine squared on both sides and got this identity also. We still call it a Pythagorean identity because it's just this one divided by cosine squared. Where again, this notation, tangent squared means take the tangent and then square it. In other words, it's a short notation, so you didn't have to write tangent in parentheses and square it to make it clear whether you're just squaring theta and then taking the tangent or taking the tangent and then squaring it. We'll just use this notation for taking the tangent and then squaring it. And then if you divide this through by sine squared, you got 1 plus cotangent squared equals cosecant squared. So these are the identities that we had so far, the Pythagorean identities and the reciprocal identities. We're going to get some more of those today and use them to solve some problems. Moreover, we found that we could evaluate these trig functions at any special angle. All right, so the trig function values, hope I'm not repeating too much, but I always like to make sure that we're up to speed before we get started with the new stuff. The trig function values are can be found exactly for any special angle. It's any angle that's multiple of 30 and 45 degrees. These are multiples of 30 degrees, which is pi over 6 we have to memorize, or 45 degrees, or both. 45 degrees is pi over 4. By means of a reference triangle. In the unit circle. So here is what's typical example. We can take all sorts of angles, but I'll take a more difficult example this time. Suppose I wanted to take theta equals negative 870 degrees. How about that? We can take and evaluate this exactly. How do we know that this is a special angle? This is a good question all by itself. How do I know it's a special angle? If it's a multiple of 30 or 45. Now you can divide on your calculator, but if you look at this, here's a trick for telling right off. If this is a multiple of 30 or 45, right? Well, you can see this is a multiple of 30 because it's divisible by 10 because it ends in 0. And so the question is just, is this number divisible by 3? Remember this trick from algebra or arithmetic? If the sum of these numbers, this number is divisible by 3, if and only if the sum of its digits is divisible by 3. So 8 plus 7 is 15 is divisible by 3. Therefore, 87 is also divisible by 3. In fact, it's 29 times 3. But you can look at this, and if the sum of the digits 15 is divisible by 3, you know this is divisible by 3. It ends in 0, so it's divisible by 30. That's a nice little trick. You don't have to use that, but I'll just give that to you in case that's helpful. So this angle is divisible by 30. It's a special angle. All right. I can evaluate all 6 trig functions exactly. I think it helps to draw this. That's how you get the reference triangle. And the reference triangle can then do this for any special angle. What is minus 870 degrees? The way you do this typically is you write it as a sum of those angles we memorize. We'll say minus 870 degrees is minus 720 plus something else. Why do I choose minus 720? Because it's two whole rotations, so I'm going to remove all the whole rotations. You memorize those first few rotations, right? One rotation is 360 degrees. Two rotations is 720 degrees, right? Just doubled. And three rotations is 1,080 degrees. If you have those memorized, then for any reasonable angle, you can look and say, well, this is between 2 and 3 rotations, so I'll take out 2 rotations. Now what's left is 150 degrees, right? So what I'll do is I'll take out the whole rotations and then see what's left. Then I'll take out all the straight angles, right? All those important angles that we memorized, the whole rotations, then all the straight angles, then all the right angles. Then I'll hopefully be, then if it's a special angle, I'll be left with a 30 or 45 or 60 degree angle left. So I'll take out all the whole rotations. That's 2 rotations. Now 150 degrees is left. I can't take out a straight angle. That'd be 180 degrees. But I can take out 90. Let's take out 90, a right angle. And then that leaves 60 left over. And again, if they're negative, you just make all these negative. If they're positive, you make them all positive. So I've taken out 2 rotations. I've taken out a right angle. And I'm left with a special acute angle, either a 30, 45, 60, or 60 degree angle, or 0, if you happen to be on an axis. Excuse me. All right, so now I can sketch this thing. And once I can sketch this, I can get the reference triangle and find out all these things exactly. So what this shows you, it doesn't matter what special angle, no matter how big, you can just always do this. Pull out all the whole rotations, all the straight angles, all the right angles, and you're always left with a special angle or 0. So in this case, you also have to go clockwise because the angle is negative, right? So let's go clockwise. 1, 2 rotations, that's 720. Now I have to go another 90 clockwise. And then 60 clockwise. Well, 60 is 2/3 of a right angle, so I split this up into 3 equal parts, and I go to here and I say, there is the terminal ray. Once you do this a bunch of times, you get this to where you can just do this in your head, actually. You can visualize it and say, well, after I take out the whole rotation, it's just 90 and 60 clockwise. And you can picture it, and I can figure these things in my head, having done this for a while. So that is my terminal ray. And now what you do, right, to evaluate any trig function exactly, is you drop the perpendicular to the x-axis. You can drop it to the y-axis, but it'll confuse people, right? All books drop it to the x-axis just by convention. And then what you do is you take the terminal ray out to the circle, the perpendicular you dropped, and the line segment along the x-axis back to the origin, and you call this the reference triangle. Right? And then the angle inside that triangle at the origin, you call the reference angle. Now, what's the reference angle on this one? It's pretty easy because, right, I've got minus 720, that was the 2 rotations. Minus 90, that was the right angle. This one here is minus 60, the fraction of a right angle, right? Well, if this is a 90-degree angle, then these two are complementary, this one and this one. So if this is 60, this must be 30 to make them add up to 90 degrees. So you say the reference angle is 90 degrees less 60 is 30 degrees. Aha, sure enough, every time you put a special angle in there, you'll be left with a triangle with special angle, or you'll land on an axis. So now that I know it's a special triangle, get the camera moved over. I have the 2 triangles that I memorized that I told you before, absolutely fundamental. These have to be memorized for the first test because they will be on there. You've got the isosceles right triangle, 45, 45, 90. We memorized the ones with the easy numbers for doing similar triangles, but For the one that fits in the unit circle, what you want is the one with hypotenuse 1 so that it fits inside the unit circle here, right? This is length 1 since it's a unit circle. And so in that case, these sides are square root 2 over 2 and square root 2 over 2 is what all textbooks put. I think it's also important to keep in mind that this is also 1 over square root 2. Sometimes that's easier to work with. You can call these sides either 1, and this is 1. And then there's the other special right triangle with a 30-degree angle, a 60-degree angle, and a 90-degree angle. And this one with the hypotenuse 1 has this side 1/2 and this side square root 3 over 2. We proved it, right? So you memorize those two triangles. You say from these, oh, we're going to use the latter one because this is a 30, 60, 90, right? If this is 30 and this is 90, at least 60 for this one. This side length must be 1/2, right? Because it's opposite the small 30-degree angle. This side opposite the bigger 60-degree angle must be square root 3 over 2. And the hypotenuse 1 fits right in the unit circle length. So here's the special right triangles that fit right in a unit circle. And now I know exactly the coordinates of this point, right? I went square root 3 over 2 left. So the x coordinate is minus square root 3 over 2. I went 1/2 down. The y coordinate is minus 1/2. That's the cosine and sine of the angle immediately. The cosine of whatever angle got you there. Remember, all coterminal angles have the same values for the trig function. It doesn't matter if you use this one, which is 210, or you use the one we got, which is minus 870. As long as they have the same terminal ray, they have the same trig functions, all 6 of them, because they have the same xy coordinates here, right? So the cosine in particular of minus 870 degrees minus square root 3 over 2, and the sine of minus 870 degrees is immediately minus 1/2. You can find all trig functions that way then. 3 dots in mathematics means therefore. So therefore, we deduce from this that the sine of minus 870 degrees on the unit circle is this number minus 1/2. Oh, I need more room. Let me squeeze this just a little. That's still on here. Sine of minus 870 is minus 1/2. Cosine of minus 870 is minus square root 3 over 2. The tangent of minus 870 is their quotient, right? It's y over x. So we say it's minus 1/2 over minus square root 3 over 2. When the 2's are both denominators, they cancel, right? If you don't want to take top times bottom over middle times middle. The minuses cancel here. And what we've got is 1 over square root 3. I'm just going to leave it that way. Your algebra teachers say write it as square root 3 over 3 for comparison purposes. But I like it like that for the following reason. Suppose I want the other 3 trig functions, cosecant, you can leave it whichever way you want. Cosecant of minus 870 now is the sign turned upside down, it's minus 2. Right? The secant of minus 870, maybe I'm going to have to erase that. Huh? Is then this one upside down, minus 2 over square root 3, and you can leave it like that if you want, or rationalize it. And then this one, the cotangent turned upside down, is just square root 3, right? So there's the 6 trig function values. Minus 870 degrees. That'll look doable. It's a little harder example, but we did things similar to that last. Okay, now sometimes a special angle will land right on an axis, right? For instance, suppose I took the angle 900 degrees, right? What happens with 900 degrees? I do the same thing. I'll break it up into whole rotations. I'll say 360, 720, 1080. This is between 2 and 3 rotations. So this is 720 degrees, and then I see what's left over, 180. And then I pull out the straight angle 180, and I've got 0 left over. I've got no fractional angle, a fraction of a right angle left over. So I just draw it as it is. I'll draw, this time it's counterclockwise, 2 rotations, 1 straight angle. You pull out the rotations, the straight angles, the right angles, and see what's left. All right, and 0 left over. So these are all counterclockwise since it's positive angles. And I just draw either with the chalk or in my mind 2 rotations. There's the 2 rotations, and then a straight angle. There it is. The terminal ray evidently is right here. And so the sine and cosine, or the cosine first actually, is the coordinates of the point, -1, 0. So we have then that cosine, I'll say sine is the y coordinate. Sine of 900 degrees is the y coordinate is 0. The cosine of 900 degrees is the x coordinate is -1. The tangent is their ratio, right? Tangent is y over x, so it's 0 over 1, -1 is 0. So these trig functions can be 0. And then the reciprocals. Cosecant is the reciprocal of sine. Is 1 over 0. Oh, we just say it's undefined. All right. The secant of 900 degrees is 1 over -1, 1 over the x coordinate, or 1 over cosine, is -1. And the cotangent is the reciprocal of the tangent, 1 over 0, or if you like, x over y, is also undefined. And what you'll find is along every axis, 2 of these are undefined. Right? Because there'll be 2 of them where you get a division by 0 when the terminal ray is on the axis. All right, we call these quadrantal angles when they land on in between the quadrants, right? There's quadrants 1, 2, 3, 4, and then between. Well, we want a couple more identities here. The quotient identities. Pretty soon I'll put a list of identities online and you can download it in case you're interested. They're also in the book, of course. We've been sort of alluding to these all along. I just haven't written them out formally. We know that tangent theta is y over x, right? That's its definition. Y over x in the unit circle. But wait a minute, y is sine and x is cosine. Also, we know that cotangent theta is x over y, x is cosine, and y is sine. These are the proofs of the quotient identities that tangent theta is sine theta over cosine theta, and the cotangent theta is the cosine theta divided by the sine of theta. Since these are quotients, they're called quotient identities. You have to memorize these too. They come up all semester. There's also a little trick. These are less important identities, but they are used frequently. If you go into the sciences or mathematics, these are still used frequently enough. The unit circle can be used to prove a lot of these identities. Here's another one, shows that suppose I take any angle whatsoever, let's call this theta, And I might take minus theta. That has to go the same measure in the opposite direction. So maybe it looks like that, right? Oops. Should look the same measure, but the opposite direction. So here's minus theta. Now suppose I wanted to compute the trig functions for this angle, no matter what it is. I'll leave it arbitrary so it constitutes a proof. If I make a specific angle, it only proves it for that angle, right? So I'll drop a perpendicular for each one. Because they're the same measure, the opposite directions, they land at the same point, right? So they land at the same point. That means they have the same x coordinate. What does that prove? Same x coordinate for the reference triangle for minus theta as for plus theta. Says what? X is the cosine. That says these two angles have the same cosine. Cosine of minus theta is the same as cosine theta. All right. How about the y-coordinates? Well, this y-coordinate, this triangle is congruent to this triangle, right? How do I know that? They have the same side length here, right? Because it's the same segment. They have the same hit length here because they're both 1. And by the Pythagorean theorem, that'll force the last side to be equal. And side is a congruence theorem in geometry. So these are congruent triangles. They have the same side measures, all three around. Let's see if I can put this over, I guess. Slow me down if I go too fast. Or tell me if you have any questions here. These get to be a lot of identities. They're all pretty straightforward, as you can see. This is a nice, easy picture. But boy, you start getting a bunch of them, they start, it's hard to remember everything. So as you need to ask me questions. It's like when I take roll at the beginning of the semester, you know, I read 3 names, I remember everybody in class, but then I read 30 names, I don't remember any of them at all. It's terrible. So I have to sit there and try and remember a couple of them at a time. So I'll try and pick up your names as we go. So we have a small in-person class. All right, so I have this. Now we notice that if this is y here, this is minus y here, right? If this is the y coordinate, this length, and this one is minus that because it's down the opposite direction. And that works in any quadrant, even though I haven't put in the details there. And consequently, we observe that sine of minus theta, that's the y coordinate here, is minus the y coordinate of sine of plus theta. That's an identity. You can do this for all the trig functions. How about the tangent of minus theta? Well, it's the y coordinate of minus theta over the x coordinate of minus theta. So it's minus y over plus x. Is minus y over x, but y over x is the tangent of theta. And you can do this for the others. Then the reciprocal relationships imply the other 3. That because cosecant is 1 over the sine. Let's write it this way. Cosecant of minus theta is 1 over the sine of minus theta. Is 1 over the minus comes out of the sine. I won't always do so many proofs, but these again, if you forget some of these identities, you can figure them out if you've seen the proofs. It's really useful. Minus 1 over sine theta is minus the cosecant of theta. What you're starting to see on all these identities is if you take cosine of minus, a trig function of minus an angle, either the minus goes away and you just get back the same as trig function of the plus the angle, or the minus comes out, right? If the minus comes out, remember what that means from algebra? What happens if the minus comes out? What happens if the minus goes away? I'll finish these other trig identities while you think about it. So the minus comes out on this one, and maybe I'll just put these without proof, but cotangent of minus theta is minus the cotangent of theta, because it's 1 over tangent and the minus comes out. And the secant of minus theta being 1 over the cosine, and the minus goes away. The minus on secant goes away also. By the way, sometimes you'll see me draw these parentheses and sometimes not. What happens is these are all functions, so technically there should be parentheses, but everybody knows the parentheses go there. It's just convention to leave them off when it's understood parentheses are there. But for the minus sake, sometimes I'll put the parentheses in to make it clear. So you can put your parentheses in or off just so it's clear whether you know, what's supposed to be in the parentheses. So we have these 6 trig identities. 1 for each of the trig functions. The minus either goes away or the minus comes out, one or the other. This should remind you of something in algebra. Did I ring a bell yet? This is going to be real important when we go to graph functions. From algebra, for functions in general, 1, if f of minus x is equal to f of x, the minus goes away, then f of x is called an even function. That sound familiar? Maybe? Yes? Remember even functions and odd functions? What's the great property about an even function? It has this nice graphical property. Suppose I know this half of the graph over here, for instance. Maybe it looks like a squiggle like that or something. If this is y equals f of x for x positive, then I know the other half of the graph. What is it? If here's x and here's y, then I have to be able to go over to minus x and get the same y, right? F of minus x is equal to plus of f of x. And so the graph over here is identical copy to that side. It has a symmetry over the y-axis, right? Because f of minus x gives you the same y as f of plus x. And the graph is symmetric over the y-axis. You just flip it over, it lands on itself. You know half the graph, you know the whole thing. Okay. That's true of any even function. What we just found is that secant and cosine are even functions. Let's write that word here, even. Off the screen up there, but even on cosine. 2, if the minus comes out. So that f of minus x is minus f of x for all x. Then f of x is said to be an odd function. And now what happens to its graph? It has a symmetry through the origin. The 0.00. Like this. And you just think about it, it has to be. Suppose this is my graph of an odd function, right? This might be like y equals x cubed or something. Maybe it's y equals x cubed. Y equals x cubed is an odd function, right? But here's y equals f of x, a generic odd function. What happens if I take any x here and I get this point f of x, y? This says that the y coordinate at minus x is minus the y coordinate plus x. So if I go over to minus x, the same distance the other side, I have to go to minus this height. F of minus x, right? F of this value has to be minus this one. So it's the same distance down here as it was up over here. Consequently, you have this symmetry. Every point over here has a sister point the same distance the other side of the origin. straight through the origin. That's the symmetry through the origin. This with this, this with this. Every point is symmetric through the origin. This tells you that every trig function is either even or odd. Sine, tangent, cotangent, and cosecant are all odd functions, right? So they all have the symmetry through origin. We're going to do graphs of trig functions later, and this will help us in our graphs quite a lot. But in the meantime, it'll help us a little for some other. But this is the interesting thing. Every trig function is either even or odd. Most functions are neither, actually, if you think about it. It's not like all functions are either even or odd. Kind of seems surprising. Wouldn't you think with these different trig functions, half would be even and half would be odd? Doesn't it seem fair or something? I mean, I kind of would have thought that just off the top of my head. But no, 4 of them are odd and 2 of them are even. The way to remember this, for me, try to give you my mnemonic devices and other things to help you remember this stuff. It's just cosine and its reciprocal or even. All the rest of them are odds. That's how I think of it. All right. So let's write that down. All trig functions are either even or odd. You either have the symmetry through the origin or the symmetry across the y-axis when you graph them. And in fact, cosine and its reciprocal, secant, are even. The others are odd. One way to remember it. Here's an example. Suppose I wanted to compute the secant minus 225 degrees. Maybe I don't like figuring negative angles. I like to do positive ones. What can I do to simplify my work? Secant is even. I just immediately change it to secant plus 225 degrees. I can drop that minus anytime I want because secant is even. Right? Well, it just goes away. Now I can measure it on the unit circle as a counterclockwise angle, if I prefer. So this allows you to do all these things with the unit circle as counterclockwise angles, if you prefer, by first using the even or odd property to take care of the minus. So 225 degrees, I'll just say here 225. I pull out all the whole rotations. There aren't any, right? Because it's not at least 360 degrees. I pull out the straight angles, 180, and then that leaves me with 45. Now I try and pull out the right angles, but there aren't any. So this is it. It's just one straight angle plus 1/2 of a right angle, right? 45 degrees is half of a right angle. So I'll draw 90 degrees, and then I'll draw halfway through this quadrant, split the two axes like that, and there's the terminal rate at 135 degrees. 90 and 45, right? Oops, I'm sorry. Sorry. 225 degrees. That's straight angle plus 180 degrees plus 45 degrees. Split the axis. There we go. 45 degrees. All right. And now I can drop the perpendicular to the x-axis, even if it's upward, and say, there's the reference triangle. Go. The reference angle is evidently 45 degrees. I figure out the sides of this are square root 2 over 2, square root 2 over 2. I like to put positive numbers on here because I think of them as side lengths. You can use negatives if you like. Lots of people do that. But then the coordinates of the point are negative and negative since we're down in quadrant 3. And if I want the secant of 200 minus 225 degrees, oh, I remember. Well, we say it's the secant of plus 225 degrees, and I can just measure it there, which is 1 over the x-coordinate here. Maybe I should call this by the other notation. Minus 1 over square root 2 minus 1 over square root 2 is the same numbers. And then the reciprocal of x is minus square root 2. So I go with a positive angle whenever I prefer. Right? Now we've got a lot of identities and they're all pretty useful for doing these homework problems. So we said this last time, I just want to remind you, we didn't get to do enough examples was the problem. Recall that we said this important principle holds. This is a problem I usually put on the first exam, and textbooks put in their homework set every time. If I know one trig function value, some angle, and a quadrant that the terminal ray is in, or we say the quadrant the angle is in also. Quadrant for its angle. We don't have to know what the angle is. We still know all 6 trig functions. Values. And I want to do a harder example than we did last time now. Well, let's start off with a similar one. Suppose I'm given that cosine theta is minus 5/13. What are the other trig function values? How can I find them? There actually is more than one way to do this. One way is to draw a triangle actually inside the unit circle. And I'm good with that. Here's a good way to do it. We have the Pythagorean identity. We know that sine squared plus cosine squared equals 1. This is our Pythagorean identity. Like the Pythagorean theorem, right, you can solve for either of these two things. If I subtract sine squared, I've got the cosine squared is 1 minus sine squared. Right? Subtract sine squared from each side. And then I can square root both sides, right? So if these two are equal, then their square roots are equal to the original numbers are equal to them plus or minus. So this says that cosine theta must be plus or minus the square root of 1 minus sine squared. The idea being from algebra, right? If x squared, we said last time, equals 4, then x can be plus or minus the square root of 4, which is plus or minus the square root, plus or minus 2. This square root means the non-negative number that has that square. And so we'll say it's plus or minus the non-negative number whose square is 1 minus sine squared. All right, so that's why the plus or minus is there, is that it can be either one of those two numbers. And I'm going to call this the Pythagorean identity solved for cosine. And I'm going to use this quite frequently. I don't want you to say, where'd that come from? It's the Pythagorean identity solved for cosine. Also, if I subtract cosine squared from each side, then I get sine squared equals 1 minus cosine squared. And if I square root that, I get that sine theta is plus or minus square root 1 minus cosine squared theta. This one I'm going to call the Pythagorean identity solved for sine. So I can use that here. Once I know one trig function, I can find the other by the Pythagorean identity solved for the appropriate other trig function. So cosine theta equals minus 5/13. I'll say immediately that sine theta is plus or minus the square root of 1 minus cosine squared theta is plus or minus the square root of 1 minus, and cosine squared means take the cosine and then square it. So you take minus 5/13, that's the cosine, and then square it. And then this takes a little bit of algebra. That's why I say if you came in with bad algebra skills, you have some problems initially. You got to make sure you're up to speed quickly. Right? To subtract these, we have to put them over a common denominator. Let me first say, is this plus or minus? I don't know. Because I haven't given a quadrant. This is the problem. You need a trig function and a quadrant for, let's say, theta in quadrant 2. Now I know in quadrant 2, I just figured out an angle over here, theta, that goes into the second quadrant. When you drop the perpendicular, x will be negative. The x one will be negative, right? So I know to keep the minus sign for quadrant 2. I'll just put minus there. Now what I've got is minus the square root, and to square a fraction, you just square the top and square the bottom, and the minus squared goes away. So this is 1 minus 25 over 169 is the square root of 13. And then to subtract, recall, you put them over a common denominator. So I write this as 169 over 169. And then I subtract the numerators, 169 minus 125, all over the common denominator, or fraction, subtraction. And so this is minus the square root of 144 over 169. And in this class, you do want to know your squares through about 13 or 14, maybe 15. It will help you. You can do these on the calculator, but it'll save you a little time if you memorize that 12 squared is 144 and 13 squared is 169. So this reduces actually to minus 12/13. You want to reduce these whenever you can. Okay. So given cosine, I use the Pythagorean identity solve for sine to immediately find sine. You don't have to do this many steps. I did extra just because we're doing it for the first time here. Now, what can I do for the other 4 trig functions? This is the way it's really easy. You find from one, you find the other with the Pythagorean identities. Then once you have sine and cosine, I'll say tangent of theta. Whatever theta is, I don't even know. I just know it's cosine. And it's in quadrant 2. Tangent theta, recall by the quotient identity, is sine over cosine. Right? So once I have these two, I actually have all 6 trig functions. Right? Because tangent theta is sine over cosine is, let's see, this one, minus 12/13 over, oops, I did this wrong. Nobody said anything. This is sine. Sine is the y coordinate. It's positive. I was thinking I was doing x coordinates. Must be too early in the morning. So it's plus for quadrant 2 for sine, plus, and we just get rid of these minuses here. Sorry about that. Plus 12/13. So sine is plus 12/13, and cosine was given to us as minus 5/13. So the minus comes out front, and you've got 12 times 13, top times bottom, over middle times middle, 5 times 13. The 13s cancel, and you get minus 12/5. There's the tangent. It's just the sine divided by the cosine. Once you're fast at this, you realize 13s are both denominators. You can just cancel them right here and minus 12/5 from there too. So I just do this to be, like I said, I'm doing extra steps on this problem. There's tangent. Given one trig function, you can find the next one by the Pythagorean identity. Once you have that, you use the quotient identity to find tangent. Then what's the last 3? Well, cotangent is the reciprocal of tangent. I just write minus 5/12. Right? I turn this one upside down. Secant is the cosine turned upside down. Instead of minus 5/13, I write minus 13/5. Right? And cosecant is the sine turned upside down. Instead of 12/13, I write 13/12. Now I've got all of them. That's how easy it is once if you just give it an angle and a quadrant, you can do this. Okay. Now let's get we stepped up a little bit. If tangent theta is minus 4/3 and theta is in quadrant 4, find the other trig functions. How about this one? Tangent and cotangent are the hardest cases, actually. Here's what I like to do with tangent. Tangent theta equals minus 4/3. There's more than one way to do this. Maybe look at the book and prefer their way if you like. What I do to figure out what the sine and cosine are from the tangent is root sum square these numbers. Take square root of minus 4 squared plus 3 squared, or you can take 4 squared plus minus 3 squared, it doesn't matter. Remember this, 3, 4, 5 right triangle, 16 plus 9 is 25, square root is 5. Whatever this root sum square of these two numbers is, one squared plus the other with the square root, is called the root sum square. We divide the numerator and denominator by that number. And then we say the minus, you can have minus the top over minus the bottom, so you could also have 4/5 over minus 3/5. It's one of those two ratios. Once you divide by the root sum square. Now what happens is tangent is sine over cosine. So either this is sine and this is cosine, or this is sine and this is cosine. It's only a difference of a minus sign. But you have to figure out which one. Which can it be? You go back to the unit circle and you say, oh, if theta is in quadrant 4, terminal rays over here, and on the unit circle, x, the cosine, is positive, and y, the sine of theta, is negative. So here I'm trying to find, and tangent, okay. And so the sine, the top one, right, tangent is sine over cosine, has to be negative. It has to be this one. This must be sine of theta, and this one must be cosine theta, being in quadrant 4. So the sine is negative and the cosine is positive. I throw this one out. There it is. If you're given a tangent or a cotangent, both of these cases, divide by the root sum square. Choose the ratio with the minus by either the original top and bottom or minus the top and minus the bottom. That puts you in the right quadrant, and then you've got sine and cosine. So we deduce from that. By the way, this arrow means implies. Means if this is true, then this is true. So this implies that the top, sine theta, is the top minus 4/5, and that the cosine of theta is 3/5. That's what we've got. This is 3/5, and this is minus 4/5, and the tangent is that. Now the last three just come as easy as can be, right? Because they're reciprocals. So that's what you can do on these. You can use these quotient theorems that tangent is sine over cosine. You can use the Pythagorean identity that sine is 1 plus or minus square root 1 minus cosine squared, and cosine is plus or minus square root 1 minus sine squared. You get one more trig function, then you can find the rest of them by these reciprocal or these quotient identities, reciprocal identities, and the reciprocal identities here are cotangent theta is the tangent upside down. Tangent was minus 4/3, so cotangent is minus 3/4. Right? Secant is the cosine upside down. Where was cosine? 3/5 minus plus 3/5, so I get 5/3. And cosecant is the sine upside down, it's minus 5/4. So these things can come out to be just nice, easy fractions. Usually they're not so easy as that. Usually you get nasty square roots in them. The way I made this so easy was picking the sides to be multiples of these Pythagorean triples. 3, 4, 5 right triangle, just scale down by make 1/5 as big, and that one is a 5, 12, 13 right triangle. Scale down to have longest side 1. All right, you think you can do that? Try those. Let's try one more actually and see if we can be experts at these. Suppose I'm given that, and you want to be able to do these for the first test, because there'll be something like this in the first test. Suppose I'm given the cosecant of theta actually is 5. Find the other trig functions. Well, I need a quadrant, right? Suppose cosecant is 5 in quadrant 2. What are the other trig functions? I've got them don't mind if I do this, you can tell me so I don't mess with you. Suppose a cosecant of theta is 5. How do I find the other ones? You've got some options here. You could use the Pythagorean identity to immediately find cotangent, right? Because 1 plus cotangent squared is cosecant squared. That will do it. Or you can use the reciprocal identity. Use whichever ones you want. I'm going to say that sine theta is 1 over cosecant theta is immediately 1/5, right? Why not do the easy thing? So I know cosecant and I know sine. Now, how can I find the rest of them? Well, once I know sine, I know that cosine by the Pythagorean identity solve for cosine is plus or minus square root 1 minus sine squared, right? And we're in quadrant 2. Again, you're thinking quadrant 2. On the unit circle, the x coordinate is negative, so cosine is negative. So I'll put quadrant 2, cosine is negative. And I minus square root 1 minus 1/5 squared. We get minus square root, and then again, how do you subtract these? You square 1 over square root of 5 gives you 1/25. To subtract these, you have to put them over a common denominator, right? This is 25 25ths minus 1/25. What we've got is minus the square root of, subtract the numerators, get 24 over the common denominator 25. And then you always have to reduce these. It's a point off if you don't reduce them. These nice calculators I told you about will reduce these automatically if you buy one of those expensive TI-89s, but again, they take longer to learn too. The bottom is clearly 5, right? 25 square root of 5, but the top needs to be reduced too, right? Because 24 is 4 times 6. It's a square times another number. You can write this as 2 square root 3, right? Square root of 4 is 2. 2 square root of 6, sorry. So I get square root of 4 is 2, and square root of 6 is just square root of 6 doesn't go any further. So it's minus 2 square root 6 over 5. How about that? And then once you know those, you know the others by reciprocal, right? And the quotient theorem. So if I know sine and cosine, I now immediately know that tangent theta is sine over cosine is 1/5 over minus 2 square root 6 over 5. The denominators 5 cancel, and I get minus 1 over 2 square root 6. How about that? Or if you rationalize it, this one you have to be careful. It might be simpler rationalized because this has a 2 and this has a 2 in it. So I multiply top and bottom by square root 6. I can rewrite this as minus square root 6 over 2 times 6. What I should really do is write it this way. Multiply top and bottom by square root 2. Minus 1 over 2. 2 steps. Minus 1 over 2. Square root 2, square root 3. If I multiply top and bottom by square root 3, I get minus square root 2 over 2 square root 3. Yeah, I guess I got to write it the other way. Let's just multiply top and bottom by square root 6. Sorry about that. Minus square root 6 over 12. Yeah, let's write it that way. Multiply top and bottom by square root 6. This will be all right too. It is just as simple. And then cotangent theta is that one upside down. This one is nicer for calculating the cotangent. Because you can just turn it upside down and get minus 2 square root 6, where this one you have to rationalize again. There we go. Cosecant, sine, cosine, tangent, cotangent, and I need secant. Secant is just the cosine upside down, so secant. Turn this upside down and get minus 5 over 2 square root 6. So those are some of the harder problems in this section. Again, this is 2 sections. It's 5.2 and 5.3, as I recall. Then there's a couple problems that essentially amount to proofs, but they're very simple, so I hate to even call them that. They're just called simplify. So partly these are just to get you to memorize the theorems. I'm going to do some straight off the homework here. You can check them when you do your homework. What if I wanted to simplify this expression? This is going to happen all through the semester. You'll find out in science, you'll get this complicated trig expression. It reduces to something very simple. We're going to see some real good examples of that soon here. What if I had cosecant theta times the tangent of theta? That simplify? Here's a good trick for these, is try writing them all in terms of sine and cosine. So that's a hint. Every trig function is either a sine or a cosine, or can be written as a quotient or reciprocal of them, right? So you use the reciprocal and quotient identities to write using sine and cosine and cancel everything you can. That's how you can simplify these things. So I'll say cosecant theta is 1 over sine. Tangent is sine over cosine. Oh, and look, the sines cancel. This is all just 1 over cosine. And now at the bitter end, when I've got everything canceled, I say, oh, 1 over cosine is more succinctly put as secant. So this product can really just be written as secant. You don't want to write it this way, right? Just like you don't want to write square root of 25. You want to write 5. You don't want to write cosecant times tangent. You want to write secant, right? So that's that'll come up quite a lot in these things. Trying to leave enough time for our practice quiz here, but I do have one more thing I want to do. The last topic for today is if this is another star, you should know. This one's not as important, but you should still know it. If you know a point on the terminal ray of an angle, then you know all 6 trig functions. You don't have to know the angle itself. You just know a point on the terminal ray, or if you know one of its trig functions, you can find all 6 trig functions. You know its trig values, sine, cosine, etc. of theta. And it goes like this. I'll just do this by example. Suppose I say minus 4, 7 is on the terminal ray of theta. Actually, I'm going to make this even easier. Let's make this minus 24. Even though it's a bigger number, it'll make it a little easier. This won't be the homework problem anymore, but it's on the terminal ray of an angle. What are its trig functions? What are its trig values? Think of it like this. This is the root sum square trick again. I'll go to, again, it really helps to draw a picture. Minus 24 for x, plus 7 for y. So I've got an angle that looks about like that. Here's the terminal ray. Here's theta. I don't know what theta it is. It's not from a special angle. Well, Well, I can still find all 6 trig functions, and here's the trick. I think of the corresponding point on the unit circle. Color chalk here. Way back in here, there's a radius 1 circle, right? And on that circle is the sine and cosine. What is that point that's on the unit circle? What are its coordinates? It's the root sum square trick again. Think of this one as being on a giant circle. What's its radius? What's the radius of that circle? Well, by the Pythagorean theorem, it's 24 squared plus 7 squared square root is this hypotenuse, right? Or we could say minus 24 squared plus 7 squared if you prefer. But it's Pythagorean theorem. This comes out to be 25 if you do it, right? And so the hypotenuse is 25. So what's this point here on the unit circle? Radius 1. You can figure it right away, right? It's the same x and y, each scaled by 25, right? This is 25 times as far out. So this point, instead of being minus 24/7, comes out to be minus 24/25. I'm sorry, 25. 7/25. Just divide by the radius here of the big circle, 25. But that's the cosine. You deduce immediately that the cosine is minus 24/25. The sine is 7/25, and the other 4 you get by the quotient reciprocal identities, right? Tangent is sine over cosine. So you take 7/25 over minus 24/25. The 25s cancel and you get minus 7/24. Then the other 3 are reciprocals, right? Cotangent theta, you turn that upside down as minus 24/7, etc. That's it for today. I want to make sure we get a few minutes to do the quiz because I'm almost running out of time here. Let's just do this. If you take out a blank piece of paper and at home, I'll just ask you to figure this on your paper and send in the answer. I'll just grade you by the answer. Send it to me by email again at dstapleton@uco.edu. And so this is 3 points. Find exactly in terms of square roots the cosine of 210 degrees on the unit circle. Now, I know a lot of your calculators will tell you this exactly, and I don't want, since I don't want just the answer, I also want to say what it is. Like if it's square root 5/7, just say what it is in terms of radicals. You don't have to be able to put it in fancy notation, just write out what it is. All right. Show exact answer, not the decimal. Show work on the unit circle. You have to email it. You can't draw the unit circle. I understand that. Just show work, let's say. All right, that's it. Then you can go when you're done with that. Find the cosine of 210 degrees.